All right. In our last discussion, we talked about how space and time are not these rigid entities that we tend to think of them to be, that they are actually bendable, flexible, that time and space will curve, if you will. And we also saw that if you move one or bend one, then you move or bend the other. To put it in other terms, what we're talking about is space-time. This is where this idea of space-time comes from. Both space and time are two sides of the same coin. And you can't bend just one side of a coin. So that is well established. That was one of the general ideas of Einstein's special theory of relativity, which was published in 1905. In 1915, Einstein published his general theory of relativity, and it takes a much broader view of the nature of space-time. Unfortunately, at the time of their publication, there wasn't a lot of technology that was, quite frankly, up to speed to put his ideas to the test. But one of these ideas was tested early on by a British astronomer by the name of Sir Arthur Eddington. Here's what the basic idea was. Einstein says that light travels through space. Well, yeah, we know that. But he goes on to say that if we curve space, then we curve the pathway of light. Think of it as like a train on tracks. If the tracks are curved, then the pathway of the train is curved. Well, how do you put that to the test? Well, first we had this idea that if you had a distant star, and then we had the sun, and then the Earth down here, that the light from that star, as it approached the sun, which represents a lot of mass and therefore a lot of gravity, would be curved because of the curvature of space-time that Einstein defines as the nature of gravity itself. Well, how do we do that? How do we prove that? Well, it turns out that we have here on Earth a satellite that is just the right distance, just the right size, so periodically it gets between us and the sun, and we have a total solar eclipse. Now, it's important to understand that in the course of a total solar eclipse, it is so dark that the stars themselves come out, that they're visible. And the idea of the experiment went like this. So here's the sun, obscured by the moon. And as it moves across the sky like so, astronomers can observe it approaching a star. And then as it moves past that star, the star would reappear on the other side. Now, if the pathway of light was straight rather than curved, it would take longer for that star to appear than if the pathway was curved. And so they watched. And sure enough, that star did appear sooner than it would have had the pathway of light been straight. So in one sense, Einstein's predictions were correct, but in another sense, they were not. That star did not reappear exactly in the time that Einstein had predicted. So they got word back to Einstein about that, and this is supposedly how the story goes. He looked at the data and he said, damn, I forgot to carry a 3. He made a math error. And once he fixed his mathematics error, it snapped right in, and lo and behold, this idea of the curvature of space and time, or space-time, was proven. This put Einstein on the front page of every newspaper in the world. He was a rock star before there was such a thing as a rock star. This radically changed our whole idea of what gravity was, as articulated by Sir Isaac Newton. Now, it's important to pause here, especially in this time of a pandemic, to again look at this nature of science and how it really does work. Einstein's idea of gravity was radically different from that of Sir Isaac Newton. For instance, Sir Isaac Newton believed that the effects of gravity were instantaneous. In other words, if the sun was to suddenly disappear, according to Newton, the Earth would immediately fly off out of its orbit. Einstein says, not so fast. For the effects of gravity to be instantaneous, that would mean that those effects are faster than the speed of light, and that is a no-no. Nothing can move faster than the speed of light. Einstein says instead, no, gravity is a wave traveling at the speed of light. And the tangible evidence was there for anyone to see. Now, did that mean that we suddenly discounted everything that Newton had to say about gravity? Well, of course not. As we discussed earlier in the semester, the Principia, the book written by Sir Isaac Newton, NASA could have used an original edition Principia to send men to the moon and back on the Apollo missions. We still use the physics of Sir Isaac Newton today. They work. We don't throw the baby out with the bathwater. What we do in science instead, when we learn something new that contravenes a detail of a previously established theory, then we modify the theory itself. We don't throw the whole thing out. That's the way it really does work. All right, so that's one of the ideas of general relativity. But there's another idea that we have to discuss. I promised that I would get you here, and I haven't missed this promise yet. Here's the most famous equation in the world. All right. Now, I can get a fourth grader to look at that and go, E equals mc squared. But remember, I said early on, I want you to look at these equations and read them in a slightly different way. The way we want to look at that is we say, there is an equivalence between energy and mass, and the conversion factor is the speed of light. Well, what the hell does that mean? Well, first let's get acquainted with this guy's lesser known half-brother. E equals delta mc squared. What's that about? Well, what we're going to do is we're going to use this formula to determine something called binding energy. Well, what is binding energy? Well, it's the energy required to hold an atom together. So we're going to do a little arts and crafts here. We're going to create a helium atom. So we're going to need 2 protons, 2 neutrons, and 2 electrons. And we're going to tally up the masses of these pieces and parts and see if we can predict what the total mass of a helium atom should be. So we need to know what the mass of a proton is. 1.67262 times 10 to the negative 27 kilograms. The mass of a neutron, 1.67493 times 10 to the negative 27 kilograms. The mass of an electron, 9.1094 times 10 to the negative 31 kilograms. Now, early on in the semester, we talked about how a proton and a neutron are roughly 2,000 times the mass of an electron. And so if anybody cares to play with these numbers on their calculator, you see that it comes out to roughly 2,000 times the mass. Also, we see neutrons have slightly more mass than protons. Okay. So now, let's tally up what we need. We're going to need 2 protons. So 2 protons. That's going to be 2 times 1.67262. That's 3.34524. 0.34524. Okay. Now I'll tally up the neutrons. .34986. And I'm not going to bother with the electrons because that's going to get us into decimal points way the hell and gone out here. So we're going to simplify this a little, and we'll just tally up these. So that should be, we'll get a grand total of 3, 3, 4, 524, 6.6951. Okay. All right. So, not counting the electrons, the mass of a single helium atom should be at least that much. At least that much. Well, let's compare that to what the actual mass of a helium atom is. So that's our predicted. Here's our actual. 6.6463 times 10 to the negative 27 kilograms. Ooh, look at that. It's less. How much less? It's missing that much mass, at least that much mass. Again, if we had counted the electrons in this, it would be even more. So where did that mass go? All right. Remember, this is what it should be at the very least. But this is what it actually is, and it's missing that much. Where did that mass go? That's called missing mass. Or actually mass defect. What happened to the mass? It got converted into energy, binding energy, the energy required to hold that helium atom together. How much binding energy did we get out of that? Well, that's where this guy comes in. So now we'll use him, the binding energy. Delta M, that's what this is. All right. And I'm going to change this to 4.88. So I move my decimal point 2 places to the right, which means the exponent's going to go down, times 10 to the negative 29. Times the speed of light squared, 3.0 times 10 to the 8th, all squared. to the left. So the X1 is going to go up. Okay, so that would be the binding energy measured in joules required to hold that helium atom together. Now that doesn't really seem to mean all that much. But we're talking about a jump between mass and energy. So for instance, if I took a 2-pound rock, which is roughly what the laboratory rock is, and I held it from a height of roughly 3 feet or 1 meter and dropped it, that would be 10 joules of energy at impact. 10 joules of energy. All right? So my jump would be from 1 times 10 to the 0 kilograms to 1 times 10 to the first joules, and so that would be a multiplier of 10 to the first power. All right? In this case, I started with 4.88 times 10 to the negative 29 kilograms, and I wound up with 4.392 times 10 to the 12th, negative 12th joules. That represents a jump of 10 to the 17th power. That's 1 with 17 zeros after it. That's a hell of a lot of bang for the buck. And that's just with a simple helium atom, 2 protons, 2 neutrons. On the other hand, you could have something like this. Uranium. Uranium-235. All right. That means that there are 92 protons in the nucleus, and a grand total of 235 nucleons. So the remainder is made up of 143 neutrons. Point being is, that's a pretty large nucleus. That's a lot of binding energy. And so when you split that nucleus, you're releasing a lot of energy. This is why nuclear power is attractive, because it is a tremendous amount of bang for the buck. Obviously, nuclear power has its problems, but that's for another discussion. All right, so this is what the binding energy piece tells us. It tells us that mass is converted into energy, that there is an equivalence between energy and mass. Now, how does that pertain to this guy here? Well, so here we are. Consider the laboratory rock. 2.2 pounds, 1 kilogram. That's why it's a laboratory rock. The laboratory rock is almost exactly 1 kilogram. And I've dropped it a bunch of times in the class, so you're familiar with it. What if we could change every last particle, every last subatomic particle in that laboratory rock into energy? Every last proton, every last neutron, electron, all the quarks that make up the protons and the neutrons, we turn them all of them into energy. How much energy would we get? Well, we use this formula. The energy would be the mass, which is 1 kilogram, times the speed of light, squared, which would be 9 times 10 to the 16th joules. Well, what is that? Well, that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16. All right, so 90 million billion joules. That's how much energy is contained in the laboratory rock, 1 kilogram. To put that into perspective, that is approximately 1,000 Hiroshimas. That's how much energy is contained in that 2.5 pound or 1 kilogram laboratory rock. Perhaps I should have been more careful when I dropped it all those times. But yeah, that's how much energy there is. So here it is. Okay. Energy, mass, speed of light. Well, what is speed? Well, isn't that distance over time? So, distance, isn't that just another way of saying space? So look what we've got contained here. Energy, mass, space and time. This covers, when you think about it, just about everything. Energy, mass, space and time. Really, what else is there? We talked about science being elegant. What is elegant? It's simple and it's comprehensive. Well, this is certainly simple, and it sure as hell is comprehensive. This is beauty that would make the angels weep. Energy, mass, space, and time. That's the story of our very existence. That's the story of everything that is. And that concludes the story that I've been trying to tell you for the past 16 weeks under the hardest of circumstances. Hope you have a good summer.